Thank you for the introduction. And first of all, I would like to thank Wonwo for the invitation. And I will be talking about black hole mimickers in light of the recently observed shadows of Sagittarius A and M87. So by black hole mimickers, I mean compact objects which do not have event horizon, but they mimic many of the properties such as shadows of black hole. So these are the images that has been observed by Event Horizon Telescope recently. So this is the images of M87 and this is the images of Sagittarius A star. And in these images, the central black region over here, the central black regions over here are what we call shadows. And I'll be focusing on this shadow part. The observation of these shadows and images by the EST have opened up a new era of observational astronomy to probe and test gravity and fundamental physics in the strong field rings. This is because it is commonly believed that the gravitational field around astrophysical compact object must be described by the Kerr black hole geometry. And therefore, the EST data or results can be used to test this hypothesis and put constraint on space-time geometries which deviates from the Kerr. So in today's talk, I'll be talking about 3 black hole mimickers and discuss whether and to what extent we can constrain these black hole mimickers using the EST results. It is to be noted that black holes cast shadow, and these black hole mimickers that which we are going to talk about also cast shadows, even though they do not have event horizon. Then one might be wondering that if it is not the event horizon that is responsible for casting shadow, then what it is? So to understand this, let us consider a shadow cast by a compact object in the simplest scenario, that is in the spherically symmetric case. Okay. So this is the lensing configuration. So this is the central compact object. This is a light source, say, and this is an observer. Now, photons from this light source are emitted and travels through the gravitational field of this compact object, undergo deflection, and some of the photons get captured by the object, and a fraction of the emitted photons may reach a faraway observer. And all the measurement by this observer is done in its sky, which we call observer sky, and this is represented by this green plane, and this green plane is perpendicular to the line joining the observer and the center of the space-time geometry. Now consider this photon. So this photon, when traveling through the gravitational field of this object, it undergoes lensing and reaches the observer, faraway observer, along this direction. So this is the actual direction of the photon. However, the observer will see that its apparent direction will be along the tangent of this photon. So the observer will see that it is coming from a point alpha beta on the celestial plane. So this is the actual direction, and this will be the apparent direction. Now we can find out this point in terms of the tangent of the geodesics at the observer location through this expression. So this is the tangent, and alpha beta is related to this tangent by these expressions. Now let us assume that the gravitational field of this compact object is given by this space-time geometry. And in this space-time geometry, if we solve the geodesic equations so we find out these separated geodesic equations. So by separated, I mean generally geodesic equations are of second order, coupled and second order. And here we integrate the geodesic equation once and find out the first order geodesic equation which are decoupled. So by separated, I means we can write down the separated equation for T, phi, theta, and R. And here B, L is the energy of the photon, L is the angular momentum, K is the Carter constant, and V is effective potential, and B is the impact parameter. And this impact parameter is, you can write in terms of two impact parameters, xi and eta. So we can think xi as a projection of this impact parameter B on the equatorial plane, and eta as a projection of the impact parameter B perpendicular to the equatorial plane. So let us now consider a simple example. We first consider the Schwarzschild black hole. So for Schwarzschild black hole, the metric functions are given by this. Now, if we plot the effective potential of for photon, then the effective potential look like this. So note that the effective potential vanishes asymptotically, and also it vanishes on the event horizon. And it has a maxima at r equal to 3m. This maxima corresponds to unstable photon orbit, and we call it a photon sphere. So, and the corresponding impact parameter is given by this expression. So for Schwarzschild black hole, it will be 3√3m. Now let us consider this schematic diagram. So in this schematic diagram, suppose this is a photon source, source of light, say, and this is the central singularity of the Schwarzschild black hole, and this is the event horizon, and this is this r equal to 3m surface, say. Now if we shoot photon from this light source towards this object with a impact parameter greater than this critical value BC, then it undergoes a turning and escape to a other side, to faraway observer, or to infinity. And this in this diagram is represented by this line. And now if we decrease the impact parameter a little bit, but keep it is still greater than the critical impact parameter BC, then the photon is turns around and escape to infinity. But before that, it winds around the r equal to 3m surface. If we increase the so that means it undergoes a strong lensing. If you increase the impact parameter still more, then it will undergo more and more winding. Now if the impact parameter is less than the critical value, then what the photon do is it simply enters the r equal to 3m sphere, and even it doesn't undergo any turning. It enters the r equal to 3m surface, and eventually get captured by the event horizon. And in this potential diagram, this photon is represented by this line. So it doesn't fill the it doesn't feel any turning by the effective potential. So then it gets captured, simply captured. So now if we shoot any photon with impact parameter exactly equal to the critical value BC, then what happens is, so this black line, what happens is the photon arrive at the r equal to 3m surface tangentially, yes, and settle down there. So, and this surface acts as a location of unstable photon or unstable photon orbits. and we call it a photon sphere. So therefore the photon sphere acts, and if we have unstable photon orbits on this surface, and if we just perturb it a little bit, then either those photon will plunge in or escape to a faraway observer. Therefore these orbits, unstable orbits, which are located on this r equal to 3m surface, are also known as critical orbits. So therefore the photon sphere acts as a means boundary between all those photons which gets captured by the event horizon or by the black hole, and all those which escape to a faraway observer. Therefore if we look from this side, okay, then what we see that we'll receive all those photons which have impact parameter greater than BC, and those photons will create a bright spot in the observer sky, and all those photons which have impact parameter less than the critical value, they will just get absorbed by the, so the observer do not receive those photons, and corresponding to those impact parameter, we have a dark point in the observer sky. So therefore if we observed, so in the observer sky, then we'll have a, if we just combine all those dark points, then we'll have a dark disk of radius BC, and this is the shadow, and it has a boundary which is a circular, and its radius is BC, simple, the critical impact parameter. Note that although the surface which separates the plunging and the escaping photons have radius 3m, in the observer sky it appears at some larger radius, 3√3m, for the Schwarzschild black hole. This is because of the bending. So this critical orbit, it's that's arrive at this surface, photon are equal to 3m surface tangentially, but in the observer sky it will appear at some greater radius. So this will be 3√3m, and this will be equal to the critical impact parameter. So therefore in order to find out the boundary of the shadow, what we need to do is we need to find out the unstable circular orbits, the critical orbits. And we here we see that these critical orbits is nothing but this corresponds to the maximum of the effective potential. Therefore from the effective potential we just first find out the so the unstable circular orbits or the critical orbits correspond to the maximum of the effective potential. So we just find out the unstable circular orbits by using these conditions. Now for the metric, we have considered the spherically symmetric metric. These two, the first two conditions, this first two condition reduces to these two conditions. Now if we solve the first equation for the Schwarzschild black hole, this gives us RPH equal to 3m. And if we put RPH in the second equation, then we find that the boundary of the shadow is simply satisfies a circle of radius 3√3m. Therefore for Schwarzschild black hole, the shadow will be a circle of or circular disk of radius 3√3m. However, so this is the in case of spherically symmetric case. So in a spherically symmetric case, whether it's equatorial plane or off equatorial plane, in all plane the radius of the unstable circular orbits will be the same, means it will be 3m. So that's why if we combine all those unstable circular orbit, then we have a sphere, and projection of that sphere onto the observer sky gives us a circular disk, and that circular disk doesn't appear at 3m, but it appears at 3√3m because of the bending of light. However, in a axially symmetric rotating space-time, the situation is a bit different, because in rotating space-time we have two kind of photon. but for the motion of photons are affected by the spin, and we have two kind of photon. All those photons which moves in a direction of the spin are known as prograde photon, and those who moves in a direction opposite to the spin are known as retrograde photons. Now, suppose if we consider a equatorial plane, then on equatorial plane itself, if we look at the retrograde and prograde photons, then the unstable circular orbits for the two kind of photons will be different, and it will be different if we consider different plane also. So therefore, in different plane, the unstable circular orbits will radius will be different. Therefore, in this case, if we just join all those unstable circular orbits, then we will not have a sphere, but we can say that we will have a deformed sphere. And projection of that sphere onto the observer sky will not be a circle, but it will be some curve which is deviated from the circle. So in axially symmetry rotating space-time, generally we have the metric functions are independent of t and phi. This implies that the equation for t and phi, we can separate the equation for t and phi we using two constant of motion, that is the energy E and the angular momentum L. Now, if sometimes the equation for r and theta can also be separated, and if we can do that using, and usually this is usually done using Carter constant, and if we can do that, then the equation for r and theta can be geodesic equation for r and theta can be written in this general form. Now, in this equation, then R acts as a effective potential. Now, capital R acts as a effective potential now. Now, from this effective potential, we find out the unstable photon orbits, and for the condition for unstable photon orbits are this. In terms of capital R, this becomes this. Now, where RPA is the radius of the unstable photon orbits. Generally, what we do is, next we just solve these two equations and find out the impact parameter, critical impact parameter xi and eta as a function of RPH. Now, for asymptotically flat space-time, it can be shown that the contour of the shadow is obtained using this. So this is the expression that I showed in the earlier. And for a rotating space-time, this in terms of the impact parameter xi and eta, this becomes this. Now, if we find out xi and eta from these equations and put it in this equation and plot a parametric plot of alpha beta using RPH as a parameter, then we get the boundary of the shadow. Now, as I said, in this case, rotating case, the boundary of the shadow will not be a circle. So therefore, if we find out, we just take square of this and add, then we find out that this quantity is a function of the unstable photon orbit radius, and this unstable photon orbit radius is different in different plane. Therefore, in this case, now the boundary of the shadow is not a circle. Typically, for a rotating case, the shadow look like this in the observer sky in the alpha beta plane. And so in this diagram, if we just project the spin of the object onto this observer sky, then that will be along this. So this will be the spin. Okay. Now, so this is the center of this space-time geometry. Now notice that the shadow is not means a circle, and its center also gets shifted along the alpha axis. Now we can find out the center, this geometric center, using this expression. And once we find out the center, what we do is we find out its total area. And to find out the total area, what we do is we just draw a vector L, say, between and L plus DL between angle phi and phi plus d phi. So this is d phi. And in terms, so this say point, this is alpha beta on the shadow curve. And in terms of alpha beta, NL phi can be written by this expression. So once we find out the center, then we draw two vector L between phi and phi plus d phi, find out this area, infinitesimal area, and integrate this and find out the total area. And we equate this total area with a circular disk of, or with a circle of average radius pi r average. And if we equate this area with this, then we get the average radius of the shadow, and this is given by this expression. Now we can also define deviation from circularity. So suppose this the circle of radius r average now will look like this, say. So it will look like something like this. So it is not a circle, but yeah, so consider it to be a circle of radius r average. So this is r average, okay. So now what we do is, at a given phi, we just find out the difference between L and r average. So this is the difference, and make it square and integrate for all phi and divide it with r average and call it deviation from circularity. So if this is non-zero, then it will be the shadow will be deviated from the circular shape. And this is basically the fractional RMS distance from the circular shape. So when we talk about, so the M87, when we consider M87 results, we use this average radius, or rather the average diameter, which is this 2 times the average radius, and the deviation from circularity to constant different black hole mimickers. But when we consider Sagittarius A star, then we use a different parameter or observable. We call this is that observable is delta, and this is a fractional deviation from source-field shadow, and this is the way this is defined in the recent Sagittarius A star paper. So the delta is defined this way. So this is fractional deviation in the diameter from that of the source-field shadow. And in terms of angular diameter, this can be written like this, where this angular diameter is simple the diameter divided by the distance of the compact object from us. And this quantity over here is the total angular diameter of the source-field shadow. So the source-field shadow has a radius 3√3m. Its diameter will be 6√2 times this, 6√3m, and its angular diameter will be 6√3m by d. So this quantity over here is the angular diameter of the source-field shadow. So when we talk about the Sagittarius A star constraining the black hole mimickers using Sagittarius A star result, we use this deviation parameter. And when we talk about M87, we use this average diameter and the deviation from circularity. Now, let us talk about now what are the observed value of this parameter for M87 and Sagittarius A star. For M87, the distance is given by this, the mass of the central object is this, and the inclination angle is 17 degrees. And according to the EST collaboration, the observed angular diameter of the shadow is 42 plus minus 3 microarc second. And the deviation from circularity, this parameter is less than 0.1. That is, That means the deviation from circularity is less than 10%. And so if we now use this angular diameter and this distance d and the mass m, then we can define or we can find out a dimensionless diameter of the shadow as observed by the EST group is given by this. So 11 plus minus 1.5. So this is this should be the observed value of the fractional dimensional diameter of the shadow. And the EST collaboration has found the spin of the M87 star to be within this range. So they have not given any strict value of the spin. So when we talk about constraining the mimickers using M87 results, we'll be using this dimensionless diameter and this deviation parameter delta C. However, for Sagittarius A star, the observed value of the angular diameter of the shadow is this, and they found that the inclination angle. So unlike M87 star, they have not provided any single value for the inclination angle, but they have said that the inclination greater than 50 degree is disfavored. So in our talk, we'll be focusing on inclination angle to be below 50 degree. And also for Sagittarius A star, they have not provided any range for the spin. So we'll be considering all possible values of the spin. And for Sagittarius A star, they found out the fractional. They just observed the observed value of the fractional deviation parameter is this. Now, in order to find out the observed value of the fractional deviation parameter, what we need is we just so if we look at here, so this for Sagittarius A star, this is observed, but we need, in order to find out delta, we need the angular diameter of the source shield shadow. And the angular diameter of the source shield shadow involved the mass of the compact object as well as the distance. So the EST group took this mass and distance from other measurement and found out delta. And they took these mass and distance measurements from two other measurements called VLTI and Keck observation. And they have provided two corresponding two sets of value for delta, and these are given by this. Therefore, from this we found that at the on sigma confidence level, this delta should lie in the range this for VLTI, and for the Keck this. Now, if we find out for this theoretically for the Kerr black hole, then for Kerr black hole we find that delta lies in this range, considering all spin and inclination angle. Therefore, it is said that the observed shadow is consistent with the one predicted by the Kerr black hole. So let us now consider the black hole mimickers that we talked about. And the first black hole mimickers we considered is a naked singularity, and the space-time geometry of this the geometry around this singularity are given by a JMN space-time. And there are two kinds of JMN space-time, JMN1 and JMN2. And JMN1 space-time is given by this, where M0 is a parameter, and JMN2 space-time are given by this, where this extra parameter is lambda. And lambda lies between 0 to 1, and we can just for this lambda, this space-time can also be written in terms of M0 if we redefine lambda using this. And for JMN2, the M0 lies between 0 and 0.5. However, for JMN1, there is M0 lies between 0 and 1. And both of these space-time are matched to the to exterior social geometry at some surface RB, at some matching radius RB, and where the ADM mass of these objects are given by this. So here we can think of there are two parameters. One parameter is for the GM in space-time, there are two parameters. One is the mass capital M and another is M naught. Now, if we plot the effective potential for photon motion in this GM in space-time, then the plot look like this. So if M naught is less than 2/3, then the plot then the effective potential diverges at the singularity, and if the effective potential, if the M naught is greater than 2/3, then the effective potential goes to 0 at the singularity, and this is the effective potential of photon for in fossil black hole. Therefore, notice that in this case, whatever be the impact parameter of photons, all those photons will get refracted by this diverging potential. Therefore, in this case, there will be no capture of photons effectively. Therefore, this case will not cast any shadow. However, in this case, note that the potential has a maxima. Therefore, corresponding we have photon sphere, and this photon sphere will capture photon having impact parameter less than the critical value. All those captured photon will again get captured by the singularity. So in this case, we'll have shadow. So in this the diagram, so for Kerr black hole, we have this central singularity, event horizon, then photon sphere. However, GMN naked singularity, we have two cases as we discussed. So in this case, we don't have any photon sphere. So this is just a singularity. And in this case, we have a photon sphere. So we have singularity and photon sphere, but no event horizon. So this case will cast shadow, and this case will not cast any shadow.
Excuse me?
Yes.
So I want to hear some motivation for this JMN naked singularity. Are they,
Okay.
I mean, they are some solution to Einstein equation or some modified
Yes.
gravity? Or,
no, to Einstein equation. They so if you go through these papers, they have shown that this space-time can be formed as an end state of a gravitational collapse of some fluid in general relativity, and let me write down what will be the equation of state of the fluid. Okay. So in this case, JMN1, so the rho is proportional to 1/r². So I forgot the exact, probably it is m naught by r square, and the radial pressure is 0, and the tangential pressure p theta is simple alpha rho, where alpha is function of m naught. Okay. For the second type of fluid, rho is again proportional to r² probably, and PR and p theta are equal, means it's isotropic, and it's something some function. So I forgot this, so you can check this from this paper. So they have shown that these two type of space-time can be formed as an end state of gravitational collapse.
Okay.
In general relativity. Mm-hmm. Okay. So we considered the spherical accretion as a simple model for spherical accretion, and found out what would be the images of the system of the naked singularity. So this is for the Schwarzschild black hole, and this is for GMN naked singularity, which have a photon sphere. So this indeed cast a shadow, and these three cases are for GMN singularities where they don't have any photon sphere. So these cases do not cast any shadow. Instead, they cast a full moon image. So let us now see what the EST group has to say about our results. So these results. So in the M87, two of the M87 papers, they have cited our works, and in the fifth paper, okay. In the fifth paper, they have said that they have cited our work and said that a naked singularity which do not have any photon sphere, they cast a full moon images with no dark region. So these kind of models are ruled out. However, in the first paper, they have admitted that there are models which are difficult to rule out because they cast a shadow that is similar to a black hole. And in line of this, they have cited our work. So here they are talking about our GMN models which cast shadow. In the recent Sagittarius A star paper, they have also provided constant for this GMN model, and they have considered this GMN1, means the first GMN which cast shadow. And as you have shown that this is fractional deviation parameter delta. So this is deviation from the source field shadow, and this is normally charged. And for GMN, this is simple M0. Okay, and we have shown that for M0 greater than 2/3, so this is 2/3, we have shadow, and the fractional deviation parameter for this case is simple 0, because the shadow in this case, in this GMN case, is nothing but the shadow of the exterior source field geometry. Okay, so therefore this case is consistent with the EST data, and this case is difficult to rule out, or it's difficult to distinguish from the source field black. The next black hole mimicker we consider is the Djipoi-Voorhees space-time, and it is a static, means non-rotating and axially symmetric vacuum solution of the in general relativity, and this is properly known as a gamma metric, and the space-time geometry is given by this. And this space-time has two parameters, the parameter m and gamma, and the parameter m is related to the ADM mass, which is monopole term, and gamma is related to the quadruple moment through this expression. Now, if we put gamma to 0, we get the flat Minkowski space-time, and if we put gamma to 1, then we get the source field black holes space-time. Therefore, gamma measures deformation of the space-time from, or deviation of the space-time from the source field metric. And this space-time has a singularity at r equal to 2m, but it doesn't have any event horizon. And in the limiting case, gamma tends to infinity. If we keep the ADM mass fixed and take gamma tends to infinity limit, then we get the Chezy-Kazun solution in Gr, and this is given by this space-time, and we call it gamma infinity space-time, Gi space-time for simplicity. Now we take this metric, studies its shadow, and put a constant on this deviation parameter gamma. Now, unfortunately, the geodesic equation in this space-time cannot be separated. Means the geodesic equation, second order coupled geodesic equation, cannot be integrated to obtain a separate first order geodesic equation. So what we do is we use our own numerical ray tracing code and produce the shadow. And the for different inclination angle and gamma value, the shadows are given by this. So note that this dashed black curve is the shadow of the source field black hole, means for gamma equal to 1. And this is for inclination angle theta equal to 90 degree. And note that the shadow gets means maximally maximum deformation when gamma is close to 0.5. Okay, and this is for inclination angle 45 degree. This is for 0 degree. So as we increase the decrease the inclination angle, the shadow gets more and more rounder. And this space-time casts shadow for gamma greater than equal to half. For gamma less than equal to half, it doesn't have any unstable circular orbits, so it doesn't cast any shadow. Instead, it casts full moon image.
I'm sorry.
Yes.
I have one question in the previous
Yes.
page.
Yeah.
Here is the equation of motion cannot be separated, means that you could not obtain the Carter's constant.
Yes. Yes. Means we can find out. We can use, since this space-time doesn't depend on t and phi, then we can use the energy E, the constant of motion, and the angular momentum L to find out the first order equation for t and phi dot. But the other two equations, r and theta, so they are coupled. We cannot separate them out using Carter constant. So that's what we do is we just take first order equation for t and phi and second order equation for r and theta and solve it numerically using our numerical ray tracing code, and we solve using fourth order Runge-Kutta method, RK method.
In that equation of motion, as theta r and theta equation are coupled.
Yeah, means we have this equation, right? And when we write out the second order equation for, say, geodesic equation for r and theta, so this equation contains also r dot and theta dot, right? So they are coupled. This also constant r dot, theta dot.
I see.
So then we cannot separate them out. So we just consider the second order equation, and then we take an observer at at asymptotic observer at some large at some distance, say r not equal to 10 to the power 4 m, and from the observer location we shoot photons with different impact parameters, and we just trace back the photons in backward in time using our numerical ray tracing code and see whether those photons get captured or they just take turn and escape to a faraway observer. Accordingly, we find out the shadow contour.
So can I ask one more question about
Yes.
the element of the equations of motion? So,
Yeah.
so mean that the system could not be integrable?
Analytically, we cannot integrate, but numerically we can.
Okay. I see. Yeah.
Okay.
Thank you.
Yeah. So let us now constant the gamma metering using M87 and Sagittarius A results. And for the M87 results, as we discussed, that we'll be using this dimensionless shadow diameter and the deviation from circularity, these parameters. So here in this first plot we have taken different inclination angle and different gamma from 0.5 to 1, and for each set of point we have found out this dimensionless shadow diameter, and this is shown in this figure. So we know that so in order to be means the shadow of the gamma metric to be consistent with the observed shadow, we should have the shadow diameter to be in this range, means 11 plus minus 1.5. So it should range from 9.5 to 12.5. Okay. So, but from the lower side you can look at, so this is always greater than 9.5, and from the higher side also it is below 12.5. So for all theta naught and gamma, we can see as far as the dimensionless shadow diameter is considered, for all gamma and theta naught, the shadow of the gamma metric is consistent with the M87 results. However, the M87 papers, they have they have found the inclination angle to be 17 degree, and this is denoted by the red dotted line. So for the 17 degree also, all gamma values are consistent. However, if we consider the the deviation from circularity, so this is shown in this plot, and note that it should be below 0.1, means the deviation from circularity is less than 10%. So therefore, in this small range, we see that this parameter range is excluded. However, if we consider the inclination angle to be 17 degree, then again all gamma values are consistent. Therefore, for 17 degree inclination, the shadow of the gamma metric is consistent with the observed shadow of M87. So in principle, means we cannot constraint, means all values of gammas are consistent. So we also considered gamma greater than 1. So here I have shown from gamma 0.5 to 1. We also considered gamma greater than 1, and we found out that for gamma greater than 1, and if we consider different inclination angle, then this angular diameter always lies in this range, and the deviation from circularity lies in this range, and this is consistent with the observed value. Now, if coming to the Sagittarius A star results, so for Sagittarius A stars, as we said, we will be using this fractional deviation parameter delta from Schwarzschild shadow for VLTI and Keck, and delta. So here we have shown, I have shown in this plot, I have shown delta for different inclination angle and gamma from 0.5 to 1.5, and in this plot from gamma 1.5 to 8. And in this plot, I have shown for gamma GI space-time. So note that from at the lower side, the delta should be greater than, for the VLTI bound, VLTI delta should be greater than minus 0.17, and for Keck it should be minus 0.14. But note that in our case, delta is always greater than the lower, means bound. So from the lower side there will be no constant, but if we consider the upper bound on delta, the observed upper bound on delta, then for VLTI it's 0.01, and this is shown by this green dotted curve, and on this side of the green dotted curve, delta is greater than 0.01, so this parameter region is excluded as far as the VLTI bound is considered. However, the Keck bound, so the upper bound is 0.05, but it is always less than 0.05. So Keck bound doesn't put any constant on gamma. Therefore, if we consider the VLTI bound, then this parameter region is excluded, and all other parameter region are allowed. However, as the Sagittarius A star paper said that the inclination angle should be below 50 degree, and this is shown by this red curve. So we focus on this region, this below this red curve. So therefore, except this left to this green curve, this all gamma and inclination angle are allowed. And although the Sagittarius A star paper doesn't have, they have not provided any constant on the deviation from circularity. So although they have not provided, we have plotted this deviation from circularity for different gamma and inclination angle. So, and this is the region which is excluded by the VLTI upper bound for delta. And this green curve, so if we consider theta naught less than 50 degree and all spin for the Kerr black hole from 0 to 1 for the Kerr black hole, and find out delta C for the Kerr black hole, then we found that we find that for this inclination angle and this spin range, the maximum deviation for the from the deformation for the Kerr black hole is 0.0374, and this is shown by this green dotted curve. Therefore, if we assume that, okay, so the observed shadow will be consistent with the Kerr, that means the observed shadow will have the deformation from circularity delta C similar to the Kerr black hole. Therefore, in order that this gamma metric is consistent with the observed value, we should have the deformation to be less than or that of the Kerr black hole. But in this range, in this small parameter region, so in this small parameter region, notice that the delta C of this gamma metric is greater than that of the Kerr black hole. So this parameter region is excluded, but all other parameter region is allowed. The last example we consider is rotating Simpson-Fisher metric, and the Simpson-Fisher metric is given by this, and this is constructed in this paper by Simpson and Fisher by replacing the R equal to 0 singularity by a non-singular minimal surface of radius R0. And it can be shown that this space-time appears or can be found as an exact solution in a class of scalar tensor Hordinsky theory of gravity. For details, look at this paper. Now, what we do next is we just use Newman-Jennings algorithm to construct the spinning version of this space-time, and the space-time is given by this. And this space-time is same as the Kerr black hole space-time, except this delta hat term. If we put R0 to 0, then this delta hat term is become 1, and we have the Kerr black hole. And if R0 is non-zero, then this black hole, this space-time is different from Kerr black hole. Now, this space-time also have horizon, and its horizon is given by delta equal to 0, and this is this. Now, we have this minimal surface R0, and we have two horizon R plus minus. Now, depending on the value of R0 and the outer horizon R plus, this space-time may either represent a non-Kerr black hole or wormhole. Now, if this minimal surface is inside the outer horizon, then we can say that this is a non-Kerr black hole because we'll have a horizon then. And if the minimal surface is outside the event horizon, then we have a wormhole. It can be shown that this rotating Simpson-Fisher metric can also be obtained as a special case of popular non-Kerr metric proposed by Johansson. So the metric functions are given by this. So it has several parameters. If we set all the parameters to 0 except 1 to be non-zero, so if we set this to be this way, then we get the rotating Simpson-Fisher metric. And the radial geodesic equation, which we need to find out the unstable circular orbits, are given by this. So note that this is same as Kerr black hole. This is same as Kerr black hole except this red term. Therefore, so when we find out the unstable circular orbits in this case, then we need to be a little bit careful, because we know that in wormhole case, wormhole throat can also be act as an effective photon location of an unstable circular orbits. Therefore, what we do is, suppose if all the unstable circular orbits lies outside the wormhole throat, then the unstable circular orbit radius condition, this translate to in terms of R in these equations. So, and this is the condition of the unstable circular orbit radius of the Kerr black hole. So this is same as Kerr black hole. So in this case, the unstable circular orbits, all those unstable circular orbits of this RSB metric is the same as that of the Kerr black hole. So its shadow will be also be the same as that of the Kerr black hole. However, we know that the wormhole throat can also act as a location of unstable photon orbit radius, and this can be seen from this equation. So suppose I consider a unstable circular orbit radius at the wormhole throat, then for that this r is rph equal to r naught, so this term vanishes. Therefore r dot equal to 0 is satisfied automatically at the wormhole throat. Now the rest two condition for unstable circular orbit radius translate to capital R through this equation. Note that these were the second order equation, first order, second order means derivative, and here we have zeroth order, first order, no second order. Now if we use this first equation and use the relation between alpha and beta, so we have alpha beta in terms of xi and eta. If you put it here, and this capital R will contain xi and eta. So this is basically xi. L over E is xi, Carter constant over E is eta. So this capital R will contain xi and eta, if we put in terms of alpha beta, then we get this equation. So this describes the unstable circular orbit radius which are located at the throat. Therefore, depending on the situation, we have these four cases as shown below. So as we said that for Kerr black hole or spinning black hole, if we look at the different plane, we have the unstable circular orbit radius will be different. So therefore, so in this equation, generally RPH will have a range from RPH say minimum to RPH maximum. Okay, so now consider this first schematic diagram. So this is this R naught surface, and this is the outer radius, and this is the unstable circular projection of the unstable circular orbit in the observer sky. So in this case we have RSB black hole, and in this case the shadow will be the same as the Kerr black hole, because in the exterior geometry the unstable circular orbit radius will be same as the Kerr black hole. In this case also we have this this is the R naught surface, the wormhole throat, and the event horizon, outer event horizon somewhere inside. So in this case we have a wormhole, and in this wormhole case also all the unstable circular orbit radius are outside, so the wormhole throat. So in this case also the shadow will be the same as Kerr black hole, but in this case, so this is RPH mean and this is RPH max. Now if the RPH means the minimum unstable radius of the unstable circular orbit radius of the exterior Kerr geometry is less than the wormhole throat, then what happens is this part of this unstable circular orbit radius becomes irrelevant, because we now have because the minimum allowed radius is R naught, this. So in this case now the shadow will be given by this part of the shadow will be given by this equation, means given by the unstable circular orbit or the exterior Kerr geometry, and this part of shadow, this part will now be given by the unstable circular orbit which are located at the wormhole throat, that is by this equation. And in this case the wormhole throat is greater than the maximum possible value of the unstable circular orbit radius of the exterior Kerr geometry. So here will the whole shadow will be given by the unstable circular orbit radius located at the throat, that is only by this equation. So now therefore we have this equation, and this is the, and yes, so we now so here this we see that when R naught is less than RPH mean, the shadow is the same as the Kerr black hole, but when R naught is greater than RPH mean, the shadow gets deviated from the Kerr black hole. So the red one is Kerr black hole, but now for the RSB metric will be this red part plus this throat part. Okay, so therefore we say that there is a critical value of R naught which we call R0C, and this is RPH mean. If R naught is less than R0C, then the shadow will be the same as Kerr black hole, and if it is R greater than R0C, then the shadow will be deviated from that of the Kerr black hole. And here I have plotted for 3 R naught values, I have plotted the shadow, and this solid this dashed black dashed curve is that is for Kerr black hole, and this solid black plus blue curve is for RSV metric, rotating Simpson-Fisher metric, and not in this case R naught is less than R0C, so the shadow is the same as Kerr black hole. But in these two cases, the shadow gets R naught is greater than R0C, so shadow is different from that of the Kerr black hole. So therefore we so in this plot we take this spin and different R naught value and find out this dimensionless shadow diameter and deviation from circularity. And as I said that the deviation from for circularity for the Kerr for the observed shadow should be less than 0.1. So here we see that this is indeed true, always less than 0.1 for the RSB metric. So there will be no constraint from the delta C. So we need to look at then the average dimensionless average diameter of the shadow, and we need to keep our spin between 0.5 and 0.94, and because this is the spin range provided by the EST group, and so in this spin range, so now we use this dimensional shadow diameter. So this should be between 9.5 and 12.5. Okay, but here we see that from the lower side there is so it is always greater than 9.5. So we have to look at the upper side, and the upper side, this 12.5 line is given by this. So then this is our allowed region. And if we just find out this R naught value, so here this R naught is 2.54 R plus, and here R naught is 3.51 R plus. So as far as the M87 result is considered, if the RSB metric, the maximum value of this parameter R naught, means the throat radius of the RSB metric lies in this range, then or below this, then its shadow is consistent with the observed shadow of M87. This is probably last slide. Yeah. Yeah. So as far as the constant from the using the Sagittarius A results is considered, so here remember we'll be using this fractional deviation parameter from VLTI and Keck bound, and unlike the M87 star, so there we had the inclination angle to be 17 degree, but here we have means the parameter is, so we don't know what will be the inclination angle in this case. It should be below 50 degree, we know that, but we don't know what it is exactly. So we have several parameters, theta naught and the spin A and R0, but we can use two parameters, right? So in order to produce the plot. So now what we do is, so we have observed that for a given spin and theta naught, the shadow diameter of the RSV metric is same as the curve when R naught is greater than less than this critical value. That means this case is this first two case. Okay, this first two case. This case is this first two case. However, in the second two case, we said that the shadow gets deviated from that of the curve, and we found that if we increase R naught beyond R0C, then the shadow diameter also increases monotonically for the RSB metric. Therefore, if we increase R naught beyond R0C, then delta, the deviation, fractional deviation parameter with the Schwarzschild shadow, that also increases monotonically. And at some point, it corresponds to the upper bound of delta, of the observed delta. And we stop there and we call it R0 max. If R naught is beyond R0 max, then the corresponding delta will be outside this upper bound, and we do not, and that is excluded. So therefore, the maximum allowed value R0 max we plot here for different inclination and spin, and we focus, and this red line is 50 inclination theta equal to 50-degree line. We focus below this line, and note that this R0 max we can calculate using either cake bound or VLTI bound. So we increase R naught, and when it corresponds to 0.01, delta corresponds to 0, we call it R0 max using this VLTI bound. And for cake bound, we do it separately. We found out R0 max separately. So this is for VLTI bound, and this is for spin 0 to 0.8, from 0.8 to 1. And note that so this parameter range, this is allowed. Okay, this is allowed. All these parameter, this inclination angle and spin and the corresponding R0 max, this is allowed. So this is R0 max. So suppose we know the exact inclination angle and spin value. Suppose we consider this point, say. Suppose we consider this point. So corresponding this point, we know R0 max. And if the object has R naught less than R0 max, then it will be, its shadow will be consistent with this VLTI bound. Similarly, we do it for cake bound also, and we found out the R0 max, and yeah, so this is the allowed range. And although the Sagittarius A paper, they have not provided any constant on the deviation from circularity. We just do it, we just plotted here it for completeness. And what we have found is, and we have done it for cake bound also, and what we have found is this deviation from circularity is always less than Kerr black hole. So if the Kerr black hole is the deviation of the Kerr black hole, Kerr shadow is consistent with the observed shadow, then the deviation delta C of the RSB shadow will also be consistent with the observed shadow. But probably, but right now there is no constant on this delta C. Probably in future we can get, and then we can refine our constant maybe. So these are my broad conclusion, and I read it to you. I leave it to you to read out, and I stop here. Thank you.
Thank you for very interesting talk and explanation of the experiment results. Are there any questions or comments?
One simple question. Can you hear me?
Yeah.
So you considered, I mean, the exact solution for rotating matrix, Kerr or another RSB matrix, right? But what about, for example, some slowly rotating case? Can you still get some analysis?
Analytic what?
I mean, comparison to the experiment.
Yeah, slowly rotating. So here I have not restricted the spin. For probably you are talking about this rotating Simpson-Visser metric.
Right,
So
right.
here we have not restricted the spin. Okay, so the spin we have considered it to be from 0 to 1. So yeah, so it will work for slowly rotating also.
But from the experiment, so is there any some constraint about A parameter?
No, no. So as far as the M87 is considered, so the EST the papers, they have kept this so this spin range to be between 0.5 to 0.94, and for Sagittarius A star they have not provided any spin value, because there are other experiments also or other observation which provides the spin of the Sagittarius A star is very means in a wide range. Some provide 0.1, some provide 0.99 up to 0.99 also. So Sagittarius, yeah, so Sagittarius A star paper, the EST paper, they have not provided any spin, means exact spin value for Sagittarius A star. So that's why we have considered it from 0 to 1, means all possible values.
Okay. Thank you.
Yeah.
I got a question. I have one question. Maybe you have discussed, but let's say, so can you distinguish between a mimicker or a different theory than GR?
Generally, so suppose so these mimickers, so the second mimicker, say this gamma metric,
Right.
so this is a vacuum solution in GR. So then this mimicker, this is vacuum solution. However, the other mimicker, say the Simpson-Visser, rotating Simpson-Visser, this is definitely not a vacuum solution in GR. But if we consider this to be a solution, say, so here, so in a scalar tensor or Hornetsky theory, then these parameters are not must be related to the theory parameter, right?
Okay.
Yeah, so if we constrain this R naught using the EST results, then we put a constant on the theory parameter also.
Okay.
Yeah, but if this parameter are not, suppose you have a black hole mimicker and we are constraining a certain parameter of the black hole mimicker, if that parameter is related to a certain theory, say, then the constraint obtained from Sagittarius A star result and M87 result should be same, right? Means because it is related to the theory, not to the individual source. But if that parameter is not related to theory, suppose it is related to in some theory, it is related to the source only, just like mass, spin, then it can have so if we constraint using Sagittarius A star and M87, then it can have different range or different values for the two source.
Okay, I see. Thank you.
Yeah.
One more question.
Yes.
So previously, I guess you consider some non-rotating analysis, and then you compare with an experiment. Is it correct?
Sorry, can you repeat it again? I cannot.
Yeah, I mean, so you as a black hole mimicker, you consider some non-rotating solution, and maybe you compare with the experiment. Is it correct?
No, yeah, it may not be correct. Yeah, so but for M87 star we have a spin range and it may not be correct, but if you look at the Sagittarius A star paper, a recent paper by EST, so and they have not provided any range, then at this point is any range for spin or any particular value for spin, then at this point yeah, we can consider we can consider a non-rotating object, and we are not also only considering. EST paper have also considered a non-rotating object and constrained them using their data. So for example, this.
Right.
For example, this. So here they have considered non-spinning black hole mimickers, and here they have considered our GMN1 and then put a constant, because at this moment we don't know means what's the spin value, exact or some tighter constant on the spin value of Sagittarius A star. So there are other observations, but they predict a wide range, means from say 0.1 to 0.99 up to 0.99.
But in this case, I mean, if you include spin in your analysis, this, I mean, plot maybe changes, right?
Yeah, it will change. It will get changed, and we try to include spin, and we try to construct the spinning version using Newman-Jennings algorithm, but we didn't succeed. But for slowly rotating, it can be done, and it has been done. And people have studied shadows. Means my collaborator, they have studied shadows, and means it doesn't change much for a slow spin.
And regarding this non-rotating black hole analysis, is there any analysis on the recent, I mean, the 4-dimensional Gauss-Bonnet something black hole?
Yeah. Sorry?
Or, I mean, Gauss-Bonnet black hole.
Gauss-Bonnet?
Yeah.
For rotating Gauss-Bonnet?
No, I mean, for non-rotating field.
Yeah, in Gauss-Bonnet, there are solution, non-rotating solution. Means vacuum and charged solution also. And people have studied shadows already and constant. And they have considered the rotating version also. But constructing rotating version is not, by solving the field equation exactly, is not possible. So people then resort to Newman-Jennings algorithm, and they just construct the rotating version and then study shadow and put possible constraints.
Okay, I see. Thank you.
Yeah, welcome.
Okay, I have an elementary question.
Yeah.
You have considered the faraway photon source. Why are we ignoring the?
No. I have not considered faraway photon source. I'm just just finding out the shadow boundary. So if I consider the image, say for example, this case. Okay. Yes. Yeah. So if you consider this kind of image, then we have to consider the photon source, right? But here we have considered a spherical accretion, a simple model for spherical accretion. And so in this case, the matter is getting radially accreted, and the accreted matter will heat up and emit photons, and the photons can be emitted from singularity to far away distance, and we collect all those photons and map or create the image. So if we consider this kind of image, then we have to consider photon source.
I see.
But I'm talking about only this boundary of the shadow. So this kind of thing. So there I'm not considering any photon source. If there is photon source, whether it's far away or close to event horizon or the surface of the compact object, then this boundary must correspond to the shadow. And depending on different emission processes, the image will be different. Okay, but the shadow boundary must correspond to this, because this is the property of the space-time. Yes, if we consider say interaction of photons with plasma or something like that, then yeah, so the case is different. Their shadow contour might get modified. So yeah.
Rajibul,
Yes.
in the formalisms, the observer is infinitely far away from the source. In the formalism, when you
Yeah.
the alpha and the beta,
Yeah.
the distance from the source to the observer is
Yeah.
infinity.
Yeah.
So if but in the nature, the distance between the source and the observer is not infinity. So there is something small.
For example, in our numerical rotation code, we have considered this r equal to 10 to the power say 4n. Okay. I tell you, and we treat this as effectively the asymptotic infinity. So this is huge, right?
I see.
Yeah. So there, the metric functions basically means, yeah. So.
Okay. And one more question is about the shape of the shadow between the black hole and the wormhole. So wormhole, the shadow of the wormhole is something different from that of the black hole, especially the inside part. Is it right? I guess that you estimate, you obtain the size of the photon sphere and the size of the shadow, boundary of the shadow, but the inside part may be different from that of the wormhole.
Boundary of the shadow, and you are saying throat.
Yes, I mean that the inside part of the shadow.
Yeah.
So the wormhole case is something different.
Yeah. It can be different. Even it may not cast any shadow for wormhole. Suppose so wormhole throat is a two-way gate, right? So suppose so in case of wormhole, if we consider the accretion, say accretion is taking place on the same side of the observer and not on the other side, then yeah, so in that case we'll have shadow. But suppose we have a accretion or light source on the other side and close to the throat, then we will not have any shadow, because because the photons which have impact parameter less than the critical value on the other side, they will just pass through the throat and come to the observer. So in that case there will be no shadow. So yeah, so in wormhole case there is this situation where it casts shadow, but it may not cast shadow always.
And one more question is that just so you know, the black hole in the galaxy have the accretion disk and also magnetic field, and
Yeah.
also the inclination angle is below the 9 degrees. So all of these effects will affect the shape of the black hole shadow.
Yes.
But maybe I'm not sure. It's maybe the error bar or allow region for the mass and the spin to be is very large. We could not actually distinguish the shape of the shadow from that of the core black hole. In this aspect, could you explain how about the research trend on the black hole shadow using the black hole in modified gravity or black hole with the additional methods? How about the trend? Could you explain about that more?
No, so there are a lot of work. There are a lot of work on shadow of black holes in modified gravity or shadow of black holes with matter. So if it and generally people do not consider interaction between photon and the background matter. So they just treat them to be non-interacting. That means they just take the space-time and study the shadow. But if it is a non-vacuum solution, then there might be interaction between the photons and the background matter, say suppose there is a plasma or something like that, then it may interact, and in that case the photon trajectories will get affected. So it will not only be defined or be decided by the background space-time, but its trajectory will get modified. So in that case, a shadow will also be different. But people do not consider this interaction. They just take the background metric and study the shadow. And as far as plasma is considered, so suppose there is accretion in plasma, and the plasma will interact with the photon. So there are several works on shadow with plasma, and they consider the interaction. And in that case, the shadow is different from the original non-plasma case.
Thank you. Thank you. Yeah. Yeah.
More questions or comments?
Okay, can I ask one more question?
Yeah.
So what if there are multiple unstable photon surfaces? Do we see some multiple shape or multiple radius of the shadow?
Multiple potential field you are seeing.
Yeah.
No, I have not used that. For example, there is a dipole metric. Means you have two black holes separated, charged black holes separated by some distance, and the space-time geometry is given by this Majumdar-Papapetrou solution. So there is a dipole metric, and yeah, so in that case, people have studied images of the system using accretion disk, thin accretion disk, and yeah, so. And shadow probably also people have studied. Yeah, probably shadow also has been studied, for this space-time. So two black holes separated by some distance, and this gravitational attraction is balanced by the electric repulsion.
Mm-hmm.
So for this space-time, so the corresponding space-time is Majumdar-Papapetrou solution. And people have studied shadow for this, but for this shadow will not be depending on the observer's inclination angle. Shadow will be, there will be two shadow, overlapping of two shadow. If the inclination angle is 0 degree, there will be single shadow, something like that, with some arc outside. So they are funny kind. Yeah. So yeah. So they have. It has been studied. And also some other kind of, so the same kind of situation, but other different space times, people have studied shadows there. But I cannot remember the exact reference for that. So I need to search.
But in the experimental side, is there any research about whether there is a fine structure in the, how to say, shadow radius, whether there is just a single line or there is a multiple line or not?
Oh no, that I don't have any idea.
Okay, thank you.
Yeah.
Okay, it's already 6 p.m. Let's thank speaker again for a very nice talk.
Okay. Thank you.